Welcome. In this session, we'll do an example where we find the maximum profit given the demand functions and cost data. The demand functions are given in the form quantity demanded equals some function of the price. QA, the demand for A, is given as 5PB minus 5PA, where PA and PB are the prices per unit for A and B. Same way QB is given in terms of PA and PB. And we are given the unit cost or average cost, which assumed to be constant, and we want to maximize the profit. So first step is to find the profit function. The revenue comes from two products. From the product A, it's QA PA. From B, it's QB PB. And so the total revenue is what we get by adding those two. The cost is $60 per unit of A. So for QA units, it's 60 QA. For B, it's 70 per unit. So for QB units, it's 70 QB. Revenue minus cost then is QA PA plus QB PB minus 60 QA plus 70 QB. This has both Q's and P's in it. We will write it purely in terms of the unit prices using the given demand equations. So substitute for QA and QB from the given demand equations, which is what I have done in this step. So substitute 5PB minus 5PA for QA in both places. 500 plus 5PA minus 10PB for QB in both places where it occurs. Now we have to do a bit of algebra. Do the multiplications. So distribute PA over both terms here, PB in this, and minus 60 here and minus 70 here. So doing that gives us a big expression in which now we combine the like terms. So there is just one term with PA squared in it, one with PB squared in it, two with PA PB, combine them, and then there is just, well, there are two terms with PA in them, combine those two. There are three terms with PB, 500 PB minus 300 PB plus 700 PB, combine those and the constant term, which gives me the profit function in terms of PA and PB. Now we will find its critical point. Find the derivative with respect to PA and PB. So let's do the derivative with respect to PA first. From the first term, minus 5PA squared, by the power rule we get minus 10PA. The second term I have minus 10PA PB. So it's PA times 10PB, which is like a constant when we differentiate with respect to PA. So derivative is 10PB. There is no PA in the third term, so I get just 0. The next term, it's minus 50 PA. The derivative with respect to PA is minus 50. And there is no PA in the last two terms, so we get just 0. For PB, I get 0 from the first term, 10 PA from the second, because it's 10 PA, which is like a constant, times PB, and then minus 10 times 2 PB from the third term, 0 from the fourth term, no PB there, and then plus 900 from the fifth term, and 0 from the last term. We set this equal to 0 and solve. This is a linear system. We will solve it by elimination. If I just add the two equations on the left, minus 10 PA plus 10 PA will be 0. So I'll have only the PB term and a constant term. 10 PB minus 20 PB is minus 10 PB. Minus 50 plus 900 is 850. We will solve this equation for PB. Minus 10 PB is minus 850. If I subtract 850 from both sides and then divide both sides by negative 10, so PB is 85. We'll plug this back in one of the two equations we have here and then solve for PA. If I plug 85 for PB in the first equation, I get minus 10 PA plus 850 minus 50 equals 0. So minus 10 PA equals minus 800. So PA is 80. The problem asked for the production levels, so we find the quantities. We're plugging in 80 for PA, 85 for PB, in our demand equations. QA equals 5 PB minus 5 PA, and QB is 500 plus 5 PA minus 10 PB. These give the quantities as 25 and 50. So that many units per week in terms of the units given originally. This concludes our example. Goodbye for now.